So what I want to do today is talk about naive set theory. So what we're going to do is we're trying to lay a foundation for mathematics. And so we're trying to think carefully about mathematical objects. And it seems like the most basic or fundamental mathematical object you might think about is a set, a collection of objects. And I call it naive because we're just going to use somewhat of an informal definition of what a set is. It comes back to Cantor. He described a set this way. He says, a set is a gathering together into a whole of definitive, distinct objects of our perception or of our thought, which are called elements of the set. And so he's saying a set's just a collection of things that you think of, right? And so, you might have as an example of a set, you could call it the set Y, which is the set of people watching this lecture. And right now, you would be an element of the set because you're watching this lecture. But most likely, your grandma is probably not an element of the set because she's probably not watching this lecture right now. Possibly, conceivably, but probably not. So that's what a set is. Although typically we're going to be concerned more with sets of numbers instead of mathematical objects. So let me just list the familiar ones. The first one is, I'll call it Z. Actually, let me begin with N. And this is called the natural numbers. And so you might think these are the numbers that nature presents to us. So this would be numbers like the number of sheep that you have. And so you have 1 sheep, or 2 sheep, or 3 sheep, etc. Well, okay, yeah, that's a good question. If you don't have any sheep, you might say you have 0 sheep. And there's actually some debate of if 0 is a natural number or not. For us, we use the convention that 0 is not natural, because if you don't have any sheep, you wouldn't be talking about sheep. So, we'll use that argument. But some include 0 as a natural number, and so you have to be careful up to the convention. Okay, you can generalize the natural numbers to the integers, and here we'll include, so this is the integers, and we'll include the 0 as well as the negatives. So as well as -1, we have 1, -1, we'll have 2, -2, etc. Going on infinitely far in both directions. And then we'll have Q will be, well, you can take ratios of these things as long as you're not dividing by 0, and that gives you the rationals. So how can you write Q? You might say Q is the collection of all, let's say M over N, such that M and N are what? Integers. And we need one more criteria. That's right, we would say N is not 0 and N is not 0 to make sure we're not dividing by 0. And then we might also include the irrationals. So that would give us all real numbers if you include the rationals and the irrationals. So these are the real numbers. And then if you want to include as well imaginary numbers and things like this, you would get C, which would be your complex numbers. And so your complex numbers are all numbers of the form A plus BI, where A and B are real numbers. And you could have one that be 0, like you could have A is 0 and B is 1, in which case you just get I. Or B could be 0, in which case you just get a real number. Okay, so these are some examples of sets. There are some other interesting sets you might want to talk about. For instance, you could talk about the set of primes. So you could talk about, we could call it P, big P, is the set of all P's that are natural numbers, such that P is prime. So we might want to define what prime means. The definition you typically see for prime is that it's only divisible by 1 in itself. right? You've probably seen this. I'm going to give you a slightly different definition. It turns out to be equivalent in this setting, but it's a little more useful to work with. What does it mean for P to be prime? P being prime means that if P divides some product A times B, then, well, what does that mean? If P divides some product, if P divides A times B, think about it like if 3 divides, well, this is where A and B are integers. Well, what can you say? Well, then P can't be broken up into 2 smaller pieces, so it can't be that sum of P divides A and sum of P divides B. Since P can't be broken up, it means P must be just dividing A, or it must be dividing P. So if P divides A times B, then P divides A, or P divides B. So this is not true for things that are not prime. So here's a non-example of this. 6 divides 4 times 9. Right? Because 4 times 9 is 36. But 6 doesn't divide 4, and 6 doesn't divide 9. Why is that? Because 6 breaks up into 2 smaller pieces, a 2 and a 3, and your 2 divides the 4, and your 3 divides the 9. So if it's a non-prime number, you can break it up into smaller pieces, and you might have that some of it divides the A and some of it divides into B. But if it's a prime number, you can't do that. So this is how I'm going to think about prime. So this is a really useful definition. Okay. So there's the set of primes. We also, I'll call it T, another significant set. This is the set of P and P plus 2, where P and P plus 2 are both prime. So what kinds of things would be in here? Well, let's pick a prime number. You have 2 is a prime number. Oh, but 2 plus 2 is 4, and 4 is not prime. So that would not be in the set T. If, however, you took a number like 3, and then a number like 3 plus 2 is 5, well, those are both prime. So that would be in T. Or if you had a number like 5 and 7, those are both in T. But 7 and 9 is not in T. So these numbers, these pairs of numbers, we call these twin primes because they come right next to each other. And we talked about this in this class before that there's infinitely many prime numbers. What may be interesting to note is it's an open conjecture. That is, it's unknown, we've been unable to prove. If or if not, there are infinitely many twin primes. So I'm hoping we'll come back to this in a little bit when we talk about number theory, and we'll talk a little more about prime numbers. But this is just another example of a set. The significant thing to say about this set is that this is not a set of numbers, this is a set of pairs of numbers. So just like you can have a set of people or sets of numbers, here we can have a set of pairs of numbers. So sets can contain all kinds of things. So I'm trying to give you a sampling of different kinds of sets. Okay. Here's 2 more we should note. I could ask, what is the set of all complex numbers such that x squared plus 1 is 0? And you could think about that set. And as you're thinking about it, you'd realize, okay, this is x squared is -1. So what squared is -1? Well, I squared is -1. So I is in there. What else is squared gives you -1? Yeah, negative I. And those would be the only two elements. And there, you know there are two by the fundamental theorem of algebra. If, however, I change the set slightly to say all real numbers, it looks like it's a very similar condition. But now there are no real numbers that satisfy this condition. And so the set, what's in it? Nothing's in the set. So you might be tempted to write just like bracket, like nothing's in there. Our notation for this will be a circle with a line through it. And we call this the empty set. The set with no elements. So it's a thing, it's a set, but it's a thing that has nothing to it. So it's a set with no elements. Okay. Any questions about sets? Well, one thing I'll add is some sets live inside of other sets. So for instance, this set lives inside of the complex numbers. So these are both complex numbers. And so you could say it's a subset, that's a notation for subset. It's a subset of the complex numbers. Or if we come back over here, we have some relationships between these guys. The natural numbers are a subset of the integers. And the integers are a subset of the rationals. And the rationals are a subset of the real numbers. And the real numbers are a subset of the complex numbers. And of course, the natural numbers are also a subset of the complex numbers, because it's a subset of something that's a subset of it. So the natural numbers also live inside of the complex numbers. Okay. Maybe the last thing I'll note then on subset is this special set right here, the empty set. What is it a subset of? Yeah, anything. Well, what does it mean to be a? So you could say, let's make this precise. So we write, so here's my definition for subset. S is a subset of T means that if you have some element that's an element of S, then it's also an element of T. Everything in S is also an element of T. But then it follows that the empty set is a subset of T for any set T. Why? Well, check. Every element of the empty set has to be an element of T. So picking the element, there are elements of the empty set, so that's satisfied. So this is one of those things that we said is vacuously true. It's an implication is vacuously true because there's no conditions to check. This is like the statement that all Martian mathematicians are, 10 feet tall. It's like, yes, because look at any mathematician from Mars, and he or she happens to be 10 feet tall. You should have checked them all. There's none to check. So the condition's satisfied. So the empty set comes out to be a subset of any set. So let's just try a little example. I'll put a set, and we can try to find out what are the subsets of it. So let's consider the set with the elements A, B, and C. So let's see if we can find the subsets. Well, we know the empty set's a subset, because it's a subset of anything. What else could be a subset? Yeah, the set that just contains A, or the set that just contains B, or that just contains C, or maybe that contains a couple of them, like A and B, or A and C, or B and C, or all of them. A, B, C. If, however, I was to change this example, and I instead consider the set that has the element A, and then the second element is the set containing B and C. Notice this is a set with two elements in it. Here we have three elements, element 1, element 2, element 3. Here we only have two elements, either A or the set containing B and C. One of the elements is itself a set. So not only can you put letters in sets or numbers in sets or pairs of numbers in sets, you can put a set inside a set. Then let's think of what a subset would be. So the subsets for this, well, one of them would be the empty set. One of them would be just the element A. One of them would be the set that contains just the set B, C. And then there's the set that contains both A and the set B, C. But, very importantly, just the element B, the set containing just B, is not a subset of that set. Because B is an element of this set, but B is not an element of this set. The set has two elements. One is A, one is the set containing B and C. So B is an element of this set, but B is not an element of this set. And so this is not a subset of that set. Comfortable with that? Okay. Let's talk about some ways we can have sets interact with each other. So you've probably seen these things before, but let's just try and formalize them a little bit. The first one is intersection. So if you have sets, say A and B, you define A intersect B to be what? Well, this is going to be the collection of all elements that are in both A and B. I should say, is that clear what I'm saying? The element has to be in both A and B. So it's not all the elements in A and all the elements in B. It's all the elements that are in both A and B. In both A and B. So maybe we can make this more precise. This is equal to, well, you could say it's all the stuff in A such that it's also in B. There you go. Or vice versa. All the stuff in B that's also in A. All the stuff that's in A and that's in B as well. And so this guy has some, oh, and then there's union. We should define union. A union B, looks like a U for union, all the elements in either A or B. So this is the collection of all the elements such that X is in A or X is in B. That might be how we try to now usually define these things. The big idea here is that intersection is related to the idea of and, which is very similar to the logical connector for and, which was an up caret. Here we have a U facing in similar direction. And for union, it's the idea of or. And we're going to see the properties for union and intersection parallel the logical operations for and or. So let's see some examples of this. So let's do some properties. The first property is that these are commutative relationships. Commutative. That is, the order doesn't matter. So for instance, A union B is the same as B union A, and A intersect B is the same as B intersect A. So how might we show this? Well, there are two ways you might try and prove this. The first is you can see this with a Venn diagram. So this isn't a proof so much as a picture to convince you it's true. This is an informal proof. And so what you can do is, well, let's prove the first relation. Let's prove the second. A intersect B is B intersect A. So you can draw some Venn diagram where you have some circles that represent the element A and B. And then you just think, what is A intersect B? Well, A intersect B is all the stuff in A that's also in B. And so right here, I have A intersect B. But then you can come along and be like, what is B intersect A? Well, it's all the stuff in B that's also in A. So it's all of this stuff, so that's B intersect A. And notice it's shaded in the same place, right? So we'll see some more sophisticated examples of this in a minute. But this is a very simple example. If you wanted to write a proof out for the second one, so let me do an orange. I wanted to write a proof out. Well, what does it mean for two sets to be equal? That's right. So let me go up and include that definition. It's a really important definition. So let me put it right here. Definition. We will say S equals T means they have the same elements. Means they have exactly the same elements. So that means two things. First of all, if you're an element of S, then you're an element of T. And if you're an element of T, then you're an element of S. But that relates to the idea of subsets. If you're an element of S, then you're an element of T. That's saying S is a subset of T. And if you're an element of T, then you're an element of S. That is saying that T is a subset of S. So to show that two sets are equal, you show that each one is a subset of the other. And you have to show it both directions. So very important. In order to do this proof, you have to show both directions. So we can do that here. We want to show that A intersect B is a subset of B intersect A. So the first, this is almost like when you have a biconditional, you have to go both directions. So first we want to show that A intersect B is a subset of B intersect A. So how would you prove that? Well, you think about it. Suppose something is in A intersect B. Suppose X lives in A intersect B. Then you just unpack what that means. Then X lives in A and X lives in B. But the logical connector and is commutative. Hence, X also lives in B, and X lives in A, right? Thus, X lives in B intersect A. And now we've shown that A intersect B is a subset of B intersect A. But we're not done yet. We also have to show that B intersect A is a subset of A intersect B. And you do that exactly the same. So I'll just put similarly. You would say if something is in B intersect A, then it's in both A and B. Hence it's in both A and B. Therefore, it's in A intersect B. So this seems a little bit excessive and tedious, but I'm trying to show you a format for how to prove two sets are equal. And like, this is utterly obvious, right? But in a few minutes, we'll see some of the less obvious. And this will give us the template of how to prove it. To prove one set is equal to another, you show that the first is inside of the second by picking some arbitrary element of the first and showing it also lives in the second. And then you show the second is inside the first by picking some arbitrary element of the second and showing it's also inside of the first. So we'll do a couple more examples of that in a second. Okay, let's get to some more properties. Okay, we said that intersection and union are commutative. Let's show that they're associative. So just like with addition, associative is just saying the order doesn't matter. You can move the parentheses around. So that's saying that A intersect B, then intersected with C, should be the same thing as first you intersect the B with the C, and then you come back and do A intersect with that. And similarly, A union B, union with C, should be the same thing as A's union with the union of B and C. So parentheses tell you the priority in order, and associative is saying, well, it doesn't matter the order. So moving on from here, we won't actually put parentheses when you have three of these, because it doesn't matter. You don't need to put them anywhere. It doesn't matter the order. But let's show that the order doesn't matter. So again, we could do a Venn diagram. Let's focus on one of these. So I'll do the first one. And it might be helpful to have two Venn diagrams. So I'm going to draw two Venn diagrams. And for one of them, I'll do the left-hand side. So one of these Venn diagrams is to represent the left-hand side of my relation. And the other Venn diagram, I'll go through the steps needed to create the right-hand side. And we're just going to show if we end up with the same area shaded in both of them. And then you label them consistently. So maybe the top one was label A, and the bottom one B and C, bottom ones B and C. And so let's think about the shading. Now there's a problem set where you can work on this, and I want you to actually show out the steps in your shading like I'm going to do right now. Because you're showing, okay, first on the left-hand side, first the parentheses say do A intersect B. So first you come in and you find the intersection of A and B. And so it's this green area. And I'll label that A intersect B. And then it says take that intersection and intersect that with C. So then you come and you intersect that with C. So right here in the middle is where you're left with, which is A intersect B intersected with C. Notice the order is different on the right-hand side. On the right-hand side, I began by intersecting B with C. And then I intersect that with A. So intersect that with A. So that's A intersect B intersect C. But the point is I end up with the same shaded region in both. But I've told a different story of how I got there. And so that shows that the left-hand side equals the right-hand side. So that's a Venn diagram argument. We could also write a proof. So proof, still doing this orange box. So how do we prove this? To show two sets are equal, we have to show each is contained in the other. So let's begin by showing the left-hand side. A intersect B intersect C is contained in A intersect B intersect C. So for this direction, you say let some element B in A intersect B intersect C. Then you unpack what that means, and you try to arrive to the conclusions also on the right-hand side. So that means that your X is in both of these guys. X is in both A intersect B, and X is inside of C. But what does it mean to be inside of A intersect B? That means that X is inside of A, and X is inside of B, and we have X is inside of C. Thus, well, if X is inside of B and C, we can say X is inside of B intersect C, and we still have that X is inside of A. And thus, since X is inside of both A and B and C, you can say X is inside of A intersect B intersect C. And so that shows that A intersect B intersected with C is a subset of A intersect B intersect C. Okay, this seems extremely tedious, but again, I'm just really trying to reinforce how we do this proof method, because we will see more examples where it'll be a little less obvious how to show equivalency, and we'll need this method. Again, we've only shown one direction, and so you would need to show the other direction. So you would need to show A intersect B intersect C is contained inside of A intersect B intersect C. And so you would do this similarly. And if those are the problems that you would actually write out how to do it. But it's very similar to the one above. Okay. Let's move to things that are beginning to get a little more interesting now. In addition to union and intersection being associative and commutative, we can ask, how do they interact? So we're going to move to seeing, just like how we thought about how or and interacted, and then we introduced this idea of negation, and have these DeMorgans laws. That's where we're headed. Same thing with sets. So here we go. What is, this is going to be our distributive law. What is A intersect B union C equal to? Well, if it's not immediately obvious, you might say, well, let's try and make a Venn diagram. Here's my A, B, C. Do you have any guesses, though? That's right. A intersects B, or A, by or I mean union, A intersect C. You should think this is analogous to saying P and Q or R is logically equivalent to saying P and Q or P and R. Because how can you satisfy both P and Q or R? It means you've satisfied P and Q, or you've satisfied P and R. So exactly analogous to that. And you can verify this with a Venn diagram. A, B, C. We'll let this Venn diagram represent the left-hand side, and this one will be the right-hand side. And you can just check it. On the left-hand side, you begin by doing B union C. So B union C is all of B with all of C. So here I have B union C. And then I intersected with A. And after intersecting with A, I am left with just this piece. So there's my A intersect, B union C. On the right-hand side, you have two pieces. You have A intersect B. A intersect B is this guy right here. A intersect B. Then you have A intersect C, which is this piece right here, A intersect C. And when you take the union of those, you end up with the same region as we had here. Here we ended up with the same region. So this is a way to verify a Venn diagram of the relationship. Or you can see it logically. Or you could do a proof like we did before, where you'd have both directions. Okay. One last idea we need, and then we can introduce DeMorgans laws, and that's the complement. So when we say the complement of a set, you just think everything that's not in that set. The problem is like, what would happen if I asked you what is the complement of the set of prime numbers? You might be like, well, it's the numbers that are not prime. But like, there are other things that are not in that set. Like grandma is not in the set of prime numbers. So should grandma be in the set, the complement of the primes? Right? Or, you know, should you have irrational numbers in there, rational numbers? You know, it's kind of tough. Like, what do you put in the complement? And so what we need to do is whenever we talk about the complement of A, we need to have in mind that A lives inside of some bigger set that we have in mind. So the complement of A inside something I'll call a universal set. It's the set that we think of A as living in, the universe we're thinking of. Like with prime numbers, we're probably not thinking of the universe where grandma lives, right? We're probably thinking of like the universe of integers or the universe of natural numbers. So inside a universal set, U. And so when you have this complement, then we can define the complement of A to be, so is defined a bar, put a bar on top to mean, sometimes people put a C, but I'll put a bar, and this will be everything in my universe that is not inside of A. So as an example, I could think of the complement of the rationals when I think of the rationals as being in the real numbers. And what would that leave me with? Yeah, the irrationals. It leaves me with all real numbers x such that x is irrational. So you'd have things like the square root of 2 or pi or e living inside of here. So things like the square root of 2 lives inside of there. However, if I asked you what is the complement of the rationals, bar on top of the q bar, the complement of the rationals, but now thought of as inside of the complex numbers, now it's going to be things of the form, well, what would be of the form? So this is in the complex numbers. So I'll be left with a bunch of a plus bi's such that what?
Either A is rational or B is not.
Well, when we define the rationals, we're thinking about real rationals. So it's everything such that it's not a real number that's rational. So it's a set of all a plus bi are real, and you don't have that a is rational. So a is not rational when your b is 0. Something like that. So you can still have like 2 plus would still be in there because that's not irrational. But things like a pi plus 0i, which is just pi, would not be inside of there. Oh, yes, it would. 2 plus 0i would not be in there because it's the complement of the rationals. So we just have to be sensitive to which universe we're living in when thinking about complements. Okay, that said, assuming we have our sets A and B being inside of some well-defined universe, let's discuss DeMorgans laws. So DeMorgan tells us what is the complement of a union. Any guesses? Okay, yeah, we could make a Venn diagram and think about it that way. So you could be like, here's your Venn diagram, and the union would be everything in these circles. So the complement of that union would be everything outside of this circle. So it'd be all this green stuff. So what's another way to write that?
Something that's in the universal set that's not A, not B.
Yeah, so it's not going to be an A. Well, that's what this is saying. It's not in A or B. Is there another way to say it? Is it the same as the complement of A union the complement of B? What would the complement of A union the complement of B be? The complement of A would be like all of this stuff. The complement of B would be like all of this stuff. Well, that's different. So this isn't it. Well, here's one way you might think about it. The complement is saying not in, so it's like a negation. Negation of A or B, like P or Q. What did that come out to be? Yeah, it's not P and not Q. So in terms of sets, this would be saying not A intersect not B. And that's right. You can take a second, convince yourself, use it in a Venn diagram that these are the same. So what the complement does, it takes the complement of each member, but then it flips union to intersection. Just like how negation flips or to and. And similarly, A intersect B, but think of the complement of that. Well, that's the complement of this right here. The complement of A intersect B is this, which we said we got by complement of A union the complement of B. So this is exactly analogous to our logic law, that the negation of A and B is the negation of A or the negation of B. I guess I should use the P's and Q's, specify I'm doing propositional logic. P and Q is not P or not Q. Happy? Okay. So there's a set. There's something analogous to the XOR function that you'll be able to think about. There's something called the symmetric difference, and these other ways of combining them, and you can prove some properties exactly analogous to these. But hopefully I've modeled the layout. What I want to do now is kind of take us to the limits of naive set theory by playing more of this idea of sets of sets. And I believe the right way to think about sets of sets is to think about the filing system on a computer, where inside of a computer you have a folder, that's like your set, and a folder contains files. Those are your elements. So inside this folder we have some elements which are your, maybe some pictures of your summer vacation or whatever it may be. But inside of a folder you can also have other folders. And those folders can have inside of them elements like files, pictures, or Word documents, or whatever. Or it might have inside of them more folders, right? So on your handout there's an image of a file, some file called S, that contains inside of it many folders. It's a folder S with many folders inside of it. So that folder S is going to be for us like our set. A folder S is our set. And so what's inside of S? Well, when you look inside of S, you have a folder named A, and we'll come back and talk about A in a second. And then you also have, if you're just looking at S, you wouldn't see everything inside of A. You would just see that there's this folder called A. And then you would see there's some folder called B. And then you would see there's some folder called, that's it. And then you have files named little s and little t. So I'm using big letters to denote folders, or in this case sets, and little letters to denote files, or here just pure elements. Now these are also elements. These sets are the elements. So this is a set of 4 elements. This is a set of 4 elements. But some of these elements happen to actually be sets themselves. So we can go and we can think about some of them. So like think about the set, the folder A. What is A really? Well, A is itself secretly a folder, maybe not so secretly. And what's inside of A? Yeah, it has folders inside of it, U and V. And U and V are secretly also sets in themselves. They're these folders, U. Inside of U, it has elements U1, U2, and U3. And inside of V, it has elements, just the element V. So if we try and put this all together, we can say S has inside of it A, which is a folder, some folder A, that contains inside of it U and V, but U is a folder, and V is a folder, and the U folder has U1, U2, U3, and the V folder has little v inside of it. Where this whole thing here, this whole set, is just one element, the folder A. And similarly, you can think about B, and what's going on inside of folder B. What is it? Yeah, it's got a lot of stuff in there, right? It's got a file B, and a file W, a file X, a file Y, and a file, that's it. And then you can think about what's going on inside of W. Well, W has inside of it some elements W1 and W2. What's going inside of X? Well, X has inside of it, what's inside of X? Nothing. So X is an empty set. So X is a folder but nothing is inside of it. So I guess I should write, it's the empty set. X contains nothing. And Y contains inside of it the element Y, and then a new folder Z. And that folder Z contains inside of it Z1 and Z2. So when I put this all together, I get that the second element of my set S is itself a folder, a pretty big one, that has inside of it the element B, and then the element W, which itself is a folder, that has W1 and W2 in it. And it has the element X, which is a folder which is empty, the empty set. And it has the element Y, which has in it the little element Y. And the folder Z, which has inside of it Z1 and Z2. And there we go. This is my second element of S, is a set that contains a bunch of sets and subsets inside of it. So this is B. And then we said that S also has S and T in it. So the point of this exercise was just to emphasize that a set can have as its elements sets. And those sets can have as their elements sets. Or they could have a set that has one of its elements is a set, and one of its elements is an element, and then another element is just a set. You know, you can have all kinds of stuff going on here. But there's no problems of having sets inside sets, just like you can put folders inside folders in your computer. Are we comfortable with that idea? Okay. Do we need space? Yeah, let's get a little more space, because what we're going to see now is just fantastic. Let's do it right here in the middle. So, you know, Cantor introduces this idea. A set is just us bringing together some objects in our mind, and it can be abstract. You can have sets of sets. You can have all kinds of foolishness. And it's like, oh, okay, this seems to be working out pretty well. And we can think about sets of numbers and other kinds of sets. And so it seems like a really foundational idea in mathematics. But turns out we're going to get ourselves into some trouble. And so to see how this works, I want us to think about the set A. And what A will be is going to be a set of sets. I'm going to say A is the set of sets with exactly one element. So with exactly one element. So like, what kind of stuff is inside of A? You know, as you start looking through A, you know, you go through A and you're like, oh, one of the elements in A is the set with the element 1. Because that's a set with one element. So he lives in A. Or like the set with the element 2. And okay, there's a lot of these. There's infinitely many of those, right? But you could also have in there like the set with the element A, the little letter A. Or little letter B, or like, you know, any letter you want. You know, you could do some, I don't know any like beta, there we go. The Greek letter beta, you know, whatever, one element. Or you might imagine in there, you have like the set with the smiley face emoji. Right? So those are all the things that live in A. Or maybe you could have the set that has inside of it a set that has multiple elements, like 1, 2, 3, or something. So there's multiple elements in the set, but this outside set has only one element inside of it, the inside set. Or you could have the set that has inside of it the set of rational numbers. So, oh no, that's more than one element. No, that's right. This is the set of rational numbers, which is an element. The element is the set of rational numbers, just as this is the set of numbers 1, 2, 3. So that's what lives inside of A. Then if you can define A that way, it's a weird set, but we've defined it. You can define B to be the set of sets with more than one element. So like, what's going to be inside of B? So inside of B, you would have the set with the elements 1, 2, because that has multiple elements in it. Or like the set with like the elements A, B. Or the set with an element 1 and then the set 1, 2. Or, etc., etc. Oh, and that's only with 2 elements. You could also have to have things with 3 elements, right? You could have like the set with 1, 2. Why not? Let's put 5 to mess things up, right? You can have that in there, because these all have more than one element to them. What else has more than one element? A has more than one element. So A is going to be living inside of B as well. But what else has more than one element? B has more than, I've shown you it has, we don't know all of the elements, but it has at least more than one. There's at least, I've listed like 5 right there. So B is going to be in here. And a bunch of stuff also. And so you might think this is kind of weird because, well, like A kind of makes sense. Like A is not an element of itself. But B is an element of itself. Like, that's incredible. B lives inside itself. Because what is in B? Everything has more than one element. And there's lots of things that have more than one element, so B meets that criteria. So we might think that's a really special kind of set. Sets that are inside of themselves versus sets that are not inside of themselves. And so we might make a new set. So here's going to be let me get a new color because it's really significant. Let me use orange for this. So let me be S to be equal to all sets that are not, like B is weird, so let me rule out B. All sets that are not elements of themselves. So like A is going to be inside of there. So like when you look at S, when you look at what's in there, like somewhere you'd have the element A. Because that is a set that is not inside of itself. But as you keep going, you'd also just have the set like 1. Because the set 1 is not inside of itself. Inside of this is the number 1, which is different than the set containing 1. Or like the set containing the integers is going to be in there. Why? Because none of the integers is the set of integers. The integers are like 1, 2, 3. None of them are Z, right? So like lots of the typical stuff's in there. But, it's a meaningful definition because like there's stuff also not in there. Like B is not in there. B is not inside of S. Okay. So here's my question. Oh, I guess we're totally out of space, but we'll do it up here. So here's my question. Is S inside of itself? Two possibilities. Let's consider them. If S is inside of itself, then, well, remember, S contains all the stuff that's not an element of itself. So if this is inside of here, then S would have the property that it's not an element of itself. So then S would not be an element of itself. Uh-oh, contradiction. That's not good. So instead, let's ask, well, what happens if S is not an element of itself? oh, then S is one of these nice sets that is not an element of itself. And we said that S is made up of all those nice sets. So hence, S should belong to S. S should be an element of S. Uh-oh. Contradiction. S contains all elements that are not elements of themselves. Is S an element of S? Well, if it is, then by the definition of S, it's not an element of itself. Contradiction. If it's not an element of S, then by the definition of S, it would be included in S. Contradiction. So if this is very confusing, think of it this way. Imagine a town where everyone either cuts their own hair or they go to the barber. And they do exactly one of these things. They either go to get their hair cut by the barber or they cut their own hair. And if they cut their own hair, they don't go to the barber, right? They only do one of these two things. It seems reasonable. Until you ask the question, well, what does the barber do? Does the barber cut his own hair? If he cuts his own hair, well, then he's going to the barber to get his hair cut. A contradiction. So he can't cut his own hair. So then you say, well, instead, maybe he can't cut his own hair, so he must go to the barber. But if he's going to, that's himself, so he's cut his own hair. Contradiction, right? So that's what's going on here. And in your problem set, I have another one similar to it you can muse about. That leads to this kind of contradiction. So, what's the problem? We got a contradiction, and so that told us somewhere along the line, we messed up. And it's like, well, how could we have possibly messed up? And it seems like we messed up somewhere along here, where we started allowing just like sets of sets, and we're really loose with our definition. I mean, go back to our original definition of what is a set. Cantor. A set is a gathering together into a whole of definitive, distinct objects of our perception or of our thought, which are called elements of the set. A set of things we think of, right? It's like much too vague. And so what we're going to do next is we're going to need to be more careful in how we define sets. And these properties will stay the same. Intersections and unions, like what we talked about, is still useful, but we need to be a little more rigorous in our definition to avoid running into this contradiction. And so what we're going to do is lay an axiomatic foundation. We're going to find some axioms of set theory, and that will then allow us to go forward without running into these kinds of contradictions. Make sense? Cool. So that's the plan for next time. At the end of the handout, I came across this quote recently that I just found to be fantastic. So Bertrand Russell, the one who discovered this contradiction, which really upset the foundations of mathematics, led to this big project in set theory. He was one of the greatest logicians of the 20th century, really big deal, but he was also known as being an outspoken atheist, critic of religion. And his daughter wrote a book after he had passed away later in life, kind of reflecting upon him in faith. And I just want to share with you the quote. I think it's fantastic. This is from Catherine Tate's book, My Father, Bertrand Russell. She says, I believe myself that his whole life was a search for God, or, for those who prefer less personal terms, for absolute certainty. Somewhere at the back of my father's mind, at the bottom of his heart, in the depths of his soul, there was an empty space that had once been filled by God, and he never found anything else to put in it. He seized on the follies which are many, and labeled them official religion, while claiming that Christians have never taken seriously the good parts of Christ's teaching. But he never dealt with it seriously either. When he wanted to attack religion, he sought out its most egregious errors and held them up to ridicule, while avoiding serious discussion of the basic message I found so liberating. For me, the belief in forgiveness and grace was like sunshine after long days of rain. No matter what I did, no matter how low I fell, God would be there to forgive, to pick me up, and to set me on my feet again. Though I could not earn his love, neither could I lose it. As I went deeper and deeper into religion, however, I found it ever more satisfying. I wished I could convince my father that it added to all I had learned from him. It took very little away. I didn't find it a denial of life, a briar patch of restrictions, but a joyful affirmation. I am come that they might have life and live it more abundantly, said Jesus. I would have liked to convince my father that I had found what he had been looking for, the ineffable something he had longed for all his life. I would have liked to persuade him that the search for God does not have to be in vain. But it was hopeless. He had known too many blind Christians, bleak moralists who sucked the joy from life and persecuted their opponents. He would never have been able to see the truth they were hiding. He should have been a saint. Perhaps he was a saint, even without the faith. God's gadfly, sent to challenge the smugness of the churches with a righteousness greater than their own. I could not have persuaded him, could not even talk to him about religion. All I could do was trust him to God's care, knowing that God loved him more than I did and would do what was best for him.